students, welcome to this lecture. In this lecture, we'll start our discussion of Charpit method, and if you recall, in previous lecture we have discussed the compatible system, and based on compatibility we discussed the method Charpit method to solve first order nonlinear PD. And in this regard, we I just want to say one more thing, that in previous lecture we have defined compatible system in way that in many of the books you will find that compatible system means every solution of the two equation are common. It means that once every solution of first PD is a solution of second PD and vice versa. And but in some book you will find that compatibility system means they have at least one solution in common. So here I am not giving, so you can take a definition of compatible system that every solutions of first equation is a solution of second equation, but the condition that box of Fg is equal to 0, that is that box of Fg equal to 0, which is Jacobian of Fg with respect to xp plus p times Jacobian of Fg with respect to zp plus Jacobian of Fq with respect to yq plus q times Jacobian of Fq with respect to zq is equal to 0. This condition is basically an integrability condition which ensure that your dz equal to p dx plus q dy is integrable, and hence we can find out by integrating this dz equal to p dx plus q dy, we can find out a surface z equal to zxy, which we call as a integral surface, which is a common solution of both the equation fxyz pq equal to 0 and gxyz pq equal to 0. And to obtain this condition, we assume that this Jacobian, which is Jacobian of Fg with respect to pq, is non-zero. So we say that whatever definition of compatibility you choose, but this box Fg is equal to 0 is an integrability condition which help us to find out a one parameter family of common solution. And here we assume that this Jacobian is non-zero, because if you you can consider this example. I will take xyz pq equal to 0 and g also the same equation, that is xyz pq equal to 0. So here we can say that Jacobian is 0, box is 0, but I cannot find out, means if the formula of form of f is complex, I cannot find out p and q in terms as a function of x, y and z. So here this Jacobian is non-zero is quite important, which help us to find out p and q in terms of x, y and z, and this box Fg is equal to 0 is an integrability condition which makes sure that this affine differential equation is an exact derivative of some function z equal to zxy. So and with the help of this compatibility, we have obtained the Charpit auxiliary equation, which is dx upon fp equal to dy by fq equal to dz by pfp plus qfq equal to dp by minus fx minus pfz equal to dq divided by minus fi minus qfz. And with the help of these auxiliary equation, we try to find out gxyz pq equal to a, which is compatible with your original fxyz pq equal to 0. So this is a given first order PD which we want to solve. Now with the help of Charpit auxiliary equation, we try to find out another first order PD involving one parameter, and we say that f and g are compatible to each other, and then we try to find out the p and q from these two equation, and then dz equal to p dx plus q dy will solve, and we will have the solution z as zxy. That is the idea of Charpit method. Now let us focus on this Charpit method and consider some example so that we can understand whatever we have discussed just now. So here, let us again discuss the general strategy of Charpit method. This I am repeating it. So first thing is, if your PD is given, you transfer all the terms from the given equation to one side, let us say left hand side, and denote all expression by f. So it means that whatever equation, so suppose your equation is given as z equal to px plus qy. So this you can write it px plus qy minus z and denote this as ff x y z p q. So you denote this as px plus qy minus z equal to 0. So this is fx y z p q is equal to 0. So once we do this, then write the Charpit auxiliary equation which we have just given, and using the value of f in first step calculate the value of fx, fy, fz, fp and fq and put these in Charpit auxiliary equation. And then this the very important step is this, that here you have to select two proper fraction so that the resulting integral may come out to be the simplest relation involving at least one of the p and q. So what we try to do, choose among these equation, you choose two in a way such that you can get a simplest expression for p or q or between p and q. So it cannot, we should not choose any equation which will give a relation between x and y. We must have involved our p or q or both. Now the simplest relation of step 4 is solved along with the given equation to determine p and q. So here in step 4 you may get a relation between pq, px, py, qx, qy, any one of them, and once we have this relation between p and q or p in terms of x, y, z, use the original equation, that is f of x, y, z, p, q equal to 0 to find out the value of q. So the other one, so it means that once we do this procedure, then we are able to find out p and q as a function of x, y and z, and then put the value of p and q in this equation, dz equal to p dx plus q dy, and we already know that these f and the new relation is compatible to each other. Using compatible, we say that this has to be integrable because we have already utilized the box of fg is equal to 0. So this has to be integrable, and then we do some workout and we solve the this equation dz equal to p dx plus q dy to find out our solution, and that solution, obtained solution contains two arbitrary parameter, and we say that the solution is two parameter family of solution and known as complete solution. So now let us move to example. So find a complete integral of 2z plus px plus qy equal to yp square. So here we have this equation. Now as we pointed out, that let us shift everything on one side and denote it by fx, y, z, pq. So let us say that 2z plus px plus qy minus yp square equal to 0. So that is fx, y, z, pq. Now in a second step, you write down the Charpit's auxiliary equation, that is dx by fp equal to dy by fq equal to dz by pfp plus qfq equal to dp upon minus fx minus pfz equal to dq upon minus fy minus qfz. F is already given to us, we can easily find out fp. So fp you can simply say that it is 2x minus 2yp, so 2x minus 2yp, dy fq is what, simply 2y, so that is written here, dz by 2fp, so you can multiply and you can simply write it here, and dp upon minus fx. If you look at fx is what, fx is simply 2p, and fy is what, fy is 2q, and fz is 2 here. So we can write it here minus fx minus p fz as 2p minus p and fz is 2. So here, so it is minus 2p and this is minus 4p. So dp upon minus 4p. Similarly, you can find out the minus fy minus qfz. The minus fy means minus 2q minus q times 2 here. So it is minus 4q. So fy is what? Fy is 2q. Fy is 2q minus p square. So 2q minus p square, because this term is also there. So 2q minus p square. So here minus p square will also be there, so that is p square. So p square minus 4q, you will get it here. Now so we have, once we have auxiliary equation, now the very important step will come into picture. Now choose among these relation in a way, choose two equation in a way such that we can simplify our p or q in terms of x and y. So here if you look at dy upon 2y and dp upon minus 4p. We can choose this and we can write dy upon 2y equal to dp upon minus 4p, and we can simply write down simplify this, and we can write 2 dy by y plus dp upon p equal to 0. Now here one thing you may note, that here I am choosing this, and it may happen that somebody else choose some other two, right? The only thing is that you should have a relation between say p as xyz or q in terms of xyz or p in terms of q. So it may happen that a given partial differential equation may have more than 2 complete integral, right? So here I am choosing one. So let us say that 2 dy by y plus dp upon p equal to 0, and when you simplify you will get p equal to a by y square by simply so once we have p equal to a by y square, now use your equation fxyz pq equal to 0, that is this, put p equal to a upon y square and solve for q. Let us say that q is given as minus z by y minus ax upon y cube plus a square upon 2y4. So p and q is already given to us. Now let us solve this. Dz equal to a by y square dx plus, now within bracket, minus z by y minus ax upon y cube plus a square upon 2y4 and dy. Now here you can simply say that you can take out y here and we can write y dz. So y dz is equal to a by y dx minus z dy minus ax upon y square dy plus a square upon 2y cube dy. Now here one thing we have to note it down, that here you have to arrange in a way such that it can be written as derivative of some known form. So here since we say that it is y dz, so it means that you collect some terms of y and z. Here we have y dz, and here if you look at it is minus z dy. So this can be collected at a same place, and here a by y dx is there, and here minus ax by y square dy. So here you collect these two and these two, and since it is involving only y and it is written with dy, so no problem, we can keep it there here. So we can write it here y dz plus z dy minus a y dx minus x dy divided by y square. So we are collecting these two, minus a square upon 2y cube dy equal to 0. So here you have to use your experience in a way such that you write your dz equal to p dx plus q dy in a way that it will come out to be derivative of some exact form, right? So it is much better if you remember some form. So here if you look at y dz plus z dy, then I can write this as z of d of zy, and here minus a y dx minus x dy upon y, I can write it as minus a d of say x by y, right? And similarly you can integrate this because it is quite easy, so we can simply integrate, and we can write it that I can write this as d by d of yz minus a d of x by y minus a square upon 2 y minus y to power minus 3 dy equal to 0. Now you integrate. So when we integrate, this will be yz, and here it is minus a by x by y, and here we have a square upon 4y square, and then one more integration constant will appear here. So here we have a relation between x, y, z involving two of the parameter a and b. This a you have obtained while solving your Charpit auxiliary equation, and when you integrate this you will have one arbitrary parameter coming to picture, that is a here, and one more parameter will come when you solve the dz equal to p dx plus q dy, and hence we have two arbitrary parameter present in your solution, and you will say that this is a two parameter family of solution of fxyz pq equal to 0, and hence we call this as a complete integral of your partial differential equation. So this is one problem. Let us consider one more problem. So here find a complete integral of p square plus q square y equal to qz. So first step, write your equation as fxyz pq equal to 0. So you write down p square plus q square y minus qz equal to 0. So first thing is you transfer everything in one side and write as fxyz pq equal to 0. So once we have this, and then you calculate, you write down your Charpit auxiliary equation, that is this. So you need to remember the form of Charpit auxiliary equation, and then once your f is given, you can easily find out f of x, that is given as 0, f of y, that is p square plus q square, f of z, that is minus q, f of p is equal to 2py, that's all, f of q equal to 2qy minus z here, and that's all. And using these derivatives, now write dx by fp, dx by fp is 2py, so dx by 2py, dy upon fq, so fq is 2qy minus z, we have written here, dz by pfp, now pfp is what, p into 2py plus q into 2, so 2q square y minus qz. Now if you look at, this is what, 2p square y plus 2q square y, and if you use the equation, this is what, 2qz, so 2qz minus qz is qz here, so we have written qz. Now dp upon minus fx is 0, minus p fz is minus q, so dp equal to pq, and dq upon minus fy, fy is p square plus q square with minus sign, minus q fz is minus q. So we can simplify minus p square minus q square plus q square, so cancel out and we have minus p square. Now we have these relation. Now if you look at here, we have quite easy pattern, so I can use many in fact, but how many we can use these and this, these two, so let us use these two, and let us say dp upon pq equal to dq upon minus p square. When you simplify, it is what, dp upon q equal to dq upon minus p, we simply cancel out this p, and when you again simplify, it is p dp plus q dq equal to 0. When you integrate, it is simply what, d of p square plus q square by 2. So here what you will have, here we have p square plus q square equal to a square, where a square is some arbitrary constant. So here you can use any constant, c1, c2, d1, d2, but let us say that for simplicity I am using a square. We will see that why this a square will help us. Okay. Now given problem, we have p square plus q square equal to a square, but this is one relation between p and q, and now you utilize your equation, that is p square plus q square y equal to qz. So p square plus q square y equal to qz. Now this value is coming out to be a square, so q is equal to a square y upon z, and once we have q, you again use this equation to find out p, so p is under root a square minus q square. Now a square minus q square is a4 y square upon z square, so we have this, so we can simplify a by z, under root z square minus a square by y square. Now here you can utilize that why we have started with a square, so otherwise it is simply under root some constant. So here we have just assumed that constant to be a square, so it is just a simplicity, just for simplicity we are taking. So p is written as a by z under root z square minus a square y square. I am taking only the positive value, you can take both positive and negative value. So now once we have, so I am just giving you a method to find out in one case when I am assuming q as a square upon y, a square y upon z, and p as the plus sign, you may take the negative sign, no problem. Now putting these value of p and q in dz equal to p dx plus q dy, we have this equation, dz equal to a by z under root z square minus a square y square dx plus a square y upon z dy here. Now if you look at here, your z is involved, y is involved, and that's all. So what we do here, looking at this term, you need to arrange your thing in a way such that it is a derivative of this kind of thing. So let us write it here, you multiply both side by z, so what you will get, z dz, right, minus a square y dy equal to a under root z square minus a square y square dx. And now you get the idea. The idea is that you divide by this under root z square minus a square y square, and you write this z dz minus a square y dy divided by under root z square minus a square y square equal to a dx. So you always look at the coefficient of dx and dy, and according to coefficient of dx and dy, you arrange your equation in a way such that it will become a derivative of some exact form. So here it is, if you look at it, is the derivative of under root z square minus a square y square. So using this, let us say that you integrate and you will get under root z square minus a square y square, and here we have a dx, so ax plus b. So we have ax plus b, you square it out and you have z square minus a square y square equal to ax plus b whole square. So we can write down equation z square is equal to a square y square plus ax plus b whole square, and this involves two arbitrary parameters. So we call this as two parameter family of solution of the PD which we have discussed, and this is a complete integral of, you can check that this is a complete integral of our first order nonlinear PD. So I hope that now things are a little bit clear. So let us consider one very special type of first order equations. Here special type of first order equation means here your fx y z pq is taking some kind of simpler form, and when it is simpler form, then your solution is also coming out to be very easy. You may remember these thing, or you can understand the procedure by which we can find out the solution in these simpler cases. So here there are four cases we are considering. So first case is that when fx y z pq involve only p and q, so it means that our equation is looking like f p comma q equal to 0. So if we have f p comma q, then here we say that in this kind of equation you have a simpler way to solve this, but let us use the Charpit method to find out that simpler way. So here your Charpit equation reduced to dxy upon fp equal to dy upon fq equal to dz upon pfp plus qfq equal to dp upon, here fx is 0, fz is 0, so dp upon 0 and dq upon 0. So here you can say that this simply means what, that your p has to be a constant. In fact, if you look at dp upon 0 means what, if you look at dp upon 0 means that if we take this as some parameter say dt, then this simply says that dp by dt is equal to 0. So it means that p is constant with respect to any parameter. So we say that p is equal to a. That is what it means, that dp by 0. It has this, you should not consider this as division by 0. It is a ratio of dp with 0. So this can be understood in a way that if you take these common ratio as some dt, where t is some parameter, then dp by dt is equal to 0, and we can say that p is constant with respect to any parameter. So we can say that p is equal to constant. So we are writing here. Similarly, you can write q equal to some constant b, right? Or then of course these constant cannot be taken as arbitrary. This a and b must satisfy the equation, that is f of p comma q equal to 0. So it means that either you use p equal to a, q equal to b, and you put the condition that f of a comma b is equal to 0, or you can say that you use only one, that is p equal to a, and find out the value of q from this equation, that f of a q equal to 0. So it is up to you. So so that you can find out q as some function of q of a, which you can obtain from here also, that if f of a b equal to 0, then from here also you can find out b as a function of a. So here we can simply say that in this case your solution is what, z equal to ax plus here because it dz equal to a, p is equal to a dx plus q is simply a dy, and when you integrate you have z equal to ax plus q of ay plus some b. If you use p equal to a and q equal to b, then what you will have, dz equal to a dx plus b dy, and when you solve it is z equal to ax plus by plus c. Now here we are getting three parameter, but it is not the case, because this a and b are not independent. In fact, they are satisfying this relation that f of a b equal to 0. So when you write this kind of relation, z equal to ax plus by equal to plus c, then f of a b are related by this, or you simply write z equal to ax plus q ay plus b. Is it okay? So you can use any of this relation, either this or this. So it means that when f of pq is equal to 0, it means that your PD is independent of x, y, z. Then you simply assume P as A and Q as B, and you can write down your solution as Z equal to AX plus QAY plus B. Is it okay? Now move on to next example based on this, that P plus Q equal to PQ. Here if you look at your equation is completely in terms of P and Q, no X, Y, Z is appears. So here when you simply solve, then you have P equal to A and Q equal to B. So here if P equal to A you assume, then you can find out the value of Q. So by A plus Q equal to AQ. So Q you can find out as A upon 1 minus A, right? So that is here. But if I again, as I said, you can assume P equal to A and Q equal to B, and if you simplify this, then A plus B equal to AB. So here also you can find out the value of B as A upon 1 minus A. So either you use this kind of thing to find out B in terms of A, or you use Q to find out use P equal to A to find out Q in terms of this. So whatever you want to use, you will have this. So here as I pointed out, you can write Z equal to AX plus A upon A minus 1 Y plus B. So this is one relation. Or if I look at, I have already given AX plus BY plus C here. Now we have already noted down that f of AB equal to 0, and by solving this we have B upon A minus 1. So here when you use this, then also we have AX plus A upon A minus 1 Y plus C. So in you can see that in both the thing your solution is matching. The only thing is that your arbitrary parameter B is now represented as C, that's all. So it means that here your solution is always linear in terms of X and Y. You can write Z equal to AX plus some constant times Y plus some B. So when your PD is independent of PQ, then you have this kind of relation. Now moving on, second type, that is f of Z PQ. Here your equation is independent of X and Y, and when you write down the Charpit equation, then here we can write dx upon fp dy upon fq equal to dz upon pfp plus qfq. And now here in last two equation, dp upon minus pfz, because fx is 0 and fy is 0. So we have dp upon minus pfz equal to dq upon minus qfz. So here since f is in, depending on z, so fz is non-zero, you can cut it out, and when you solve this we have p equal to aq. So one relation p equal to aq comes, and using this and the problem means the original PD, you can solve p and q, and you can find out dz equal to pdx plus q dy. So here we can write aq dx plus q dy. So you need to find out only q, that we can find out using the first order PD, and we can find out our relation. Now let us take one example based on this, z equal to p square minus q square, and we want to find out our complete integral. So here it is independent of x and y. So here our relation is p equal to aq. You can simply put it here, and we can simply say that p equal to aq, and you can find out the value of q here. So p square minus q square minus z equal to 0. When you put p equal to aq, so you can get your q like a square q square minus q square equal to z. So q square is basically z upon a square minus 1. So you can write it under root of this plus minus. So q is basically plus minus under root z upon a square minus 1, and then p is also written as a plus minus a under root z upon a square minus 1. Then you solve your dz equal to pdx plus q dy. So now you simply see that in numerator we have under root z, that you can put it at that side. So we can write plus minus under root z upon a square minus 1 a dx plus dy, and by putting root z here we have z to power minus 1 by 2 dz equal to this quantity. So when you simplify, you will simply get z equal to b plus minus 1 upon under root 2 a square minus 1 ax plus y whole square. So here this integrating this is quite easy, because it is simply integrating, no problem. So this is the required solution. So in this case, when f z p q equal to 0, you simply write p equal to aq, and using this you can solve to find out both p and q, and then you integrate it. Is that okay? And we have a complete integral like this. Now in third, which is the case of separable equation, here your equation is not involving any z, and it can be separated out in two form, that f of xp equal to g of yq. So it can be written like this. So it means that here f of x y p q equal to 0 can be written as f of xp equal to g of yq. So you can separate it like this. Now in this case, when you write down the Charpit equation, then here dx by fp equal to dy. So here fxp minus gyq equal to 0, that is your fxyp. So fx dx by fp is nothing but small fp equal to dy upon minus gq equal to this thing. You write down your Charpit equation, and now if you simplify here, now if you simplify dx upon fp and dp upon minus fx, and then what you will get, dp upon dx plus fx upon fp equal to 0, and when you solve this, this is what, fp dp plus fx dx. So we have fp dp plus fx dx equal to 0, means what, it is d of fx comma p equal to 0. So it means that your f of xp is a constant value. If fxp is constant, so gyq is also constant, the same constant. Now with this two relation, you find out p and q. That is the idea. So it means that when your equation is separable, then your these value is just coming out to be a constant, and with this you can find out p and q, and once we have p and q, you can solve dz equal to p dx plus q dy. So let us take one example. So here p square q x square y equal to p square plus q. Here it may not be so obvious that it is a separable equation, so you have to work it out. You simply say that it is p square q divided by p square q, and when you divide, you will be written as x square plus y square equal to 1 by q plus 1 by square. Now you can simplify, and you can write x square minus 1 by p square equal to 1 by q minus y square, and as we have pointed out, these two are coming out to be constant. So x square minus 1 upon p square is equal to constant, 1 upon q minus y square is equal to the same constant. So we can solve for p and q, and p is coming out to be plus minus 1 upon under root x square minus a, and q is coming out to be this. You write down dz equal to p dx plus q dy, and when you write down, we have this equation, and this is simple, quite easy. Dz equal to some integral, this you can integrate, and here also you can integrate, and you can write down your solution as z equal to ln modulus of x plus under root x square minus a plus 1 upon under root a tan inverse y by root a plus some integration constant. So this is the solution. So in case of separable equation, you separate it out and equate the constant value. So here you write f of xp equal to g of yq, and that a constant value, that is it, right, and then integrate. You from this you find out p and q, and you can integrate this. Now in the very important part, or we can say it is quite common equation, that is Clairaut equation. So here a first order PD is said to be a Clairaut type if it can be written in the form z equal to px plus qy plus f of pq. So here if you look at your x, y, z, pq, everything is here, but it is a kind of a particular form, z equal to px plus qy and the component which involves only p and q. So this is linear part in x, y, z and pq, and linear in x, y, z, and non-linear maybe in p and q. So if you write down the corresponding Charpit equation, then here we can say that here we have dp upon 0 equal to dq upon 0. So it means that here if you look at fx is equal to what, p, fy equal to q, and fz is equal to minus 1. So we are taking this as px plus qy plus f of pq minus z. So here if you look at minus fx minus pfz, so you will get what, minus fx is minus p, and this is minus 1. So you will get 0. So dp upon 0, dq upon 0. So here you can say that your p equal to a and q equal to b, you can kind, but this a and b again it will satisfy this equation. So we simply say that pq satisfy this equation. So it means that your equation will be what, z equal to ax plus by plus f of ab, and if you look at, this is a relation between x, y, z involving two parameter, and hence we can call this as a complete integral. Is it okay? So here what we did, we have obtained p equal to constant, q equal to constant, and when you put it back, because here I cannot choose both as constant because a and b cannot be an arbitrary constant. So, a and b must satisfy the PD. Now, when you put it back into PD, then it is a relation between x, y, z and involving two parameters, that is a and b. So, it will be your the complete integral. Here you need not to solve dz equal to p dx plus q dy. That is the important part here, because here a and b are not independent, so they must satisfy the PD. When you put it back to PD, then you see that it is not involving any of p and q, it is simply written a relation between x, y, z and two arbitrary parameters. So, it will come out to be your complete integral. You need not to solve dz equal to p dx plus q dy and so on. So, that is the idea here in clarity equation. Okay. So, let us take one example based on this. Find complete integral of this equation p q z equal to this. Again, it may not look like that it is a clarity equation, but you have to simplify. So, divide by p q. When you divide by p q, you can see that it is z equal to p x plus q y plus p square upon q plus q cube upon p square. So, it is linear in x, y, z and maybe non-linear in terms of p and q. So, when you since it is claret form, you simply write p equal to a and q equal to b, and once we have p equal to a and q equal to b, you simply put it here, and you can write our solution as z equal to ax plus by plus a square upon b plus b cube upon a. So, with this I will end my discussion. In fact, in this lecture what we have discussed, we have discussed some example based on Charpit method and how we can utilize Charpit method to find out the complete integral of a given first order nonlinear PD. And also we have seen some special cases where your Charpit equation will give you a very easy answer, and we can get our solution in a very quick manner. And these are very common in in problem. So, we utilize Charpit method and these 4 special type of PDs. So, with this I end here, and thank you for listening us. Thank you.